Hi guys, welcome to this next session on radioactive decay. So what we're going to do today is we're going to describe the properties of radioactive decay, ionizing radiation. We're going to link the properties of ionizing radiation to the structure. We're going to identify the type of radioactive decay from a source. So whenever we're talking about radioactive decay, first thing we need to start off is at this thing, which is a nucleus. So nuclei can be incredibly unstable, and usually the reason why they're unstable is because they're isotopes. So if you remember that from the first video, an isotope is an atom from an element that's got the same number of protons but a different number of neutrons. Isotopes usually decay because they're very, very unstable. Now, as I said, the important thing is to do with the nucleus. The nucleus is where radiation comes from. There are 4 different types of ionizing radiation you need to know about. Little jiggle. This one. That one. That. One more. Cheeky. Right, so these 3 here at the top, they're the most important ones, and the one at the bottom, not that important. So this one here is alpha, Greek symbol alpha. This one is beta. The third one is gamma. This one over here is just a neutron. We'll talk more about the neutron at the end. So alpha, a few properties about alpha. First off, it is made from 2 protons, positive, 2 neutrons, neutral. So it has a charge of +2. Alpha is really, really big. It's literally a chunk of the nucleus that's been lobbed out. Some people also describe alpha, instead of saying that it's 2 protons, 2 neutrons, the way they describe it is they just say it's a helium nucleus. It's really important that you say a nucleus and not a helium atom, because this doesn't have any electrons orbiting it. A few properties about alpha. So as you said, charge is +2. It is incredibly ionizing. In terms, that means it's very easy to turn an atom into an ion by removing an electron. In terms of biology, it means that it can damage DNA, which then leads to mutations, which leads to things like cancer. It's got a very, very short range. Because it's so big, it can't travel very far. In air, a few centimeters. In terms of what it can travel through, it's usually stopped by paper very, very easily, air and skin. So relatively speaking, alpha is both quite dangerous and quite safe at the same time. It's quite dangerous as it's really ionizing, but it's safe because you can easily stop it. Beta. Beta again is emitted from the nucleus. We'll talk about this more next time, but it comes from the nucleus. It's not an electron from the outer shell. It is a fast moving electron. You have to say fast moving. It's got a lot of kinetic energy. It has a charge of -1 because it's literally just an electron. It can go quite far. In air, it can go about 30 centimeters to a meter. It can be stopped by aluminium. We normally say that 3 to 5 millimeters of aluminium. In terms of ionizing strength, it's not as ionizing as alpha. Then we've got gamma. Now gamma is an electromagnetic wave. It's got a high frequency. It carries a lot of energy. Charge of it, 0. I mean, it's an electromagnetic wave. It's got no charge. It's also got no mass whatsoever as well. So out of all of these, alpha is the heaviest, then beta, then gamma, which doesn't have a mass. Charges, alpha is the highest, then beta, then gamma. Gamma is very weakly ionizing. So again, in order from high to lowest ionizing strength, alpha is the highest, then beta, then gamma. In terms of how far it can travel, well, technically it can travel a very large distance. In air, it's pretty much infinite. It can travel through a vacuum. It can be stopped. Well, it can't really be stopped. It can be reduced. We say it can be reduced by meters of concrete. and lead. Depends on the activity of it, but it can reduce it to quite a low level. Sometimes it can go through lead no problem. When you store a radioactive source, you normally store it in lead, and then you may have it in something surrounded by concrete. Or if you have radioactive waste, they usually put a ceramic or concrete around it. And then neutron. Most people don't talk about neutrons that much. Neutrons mainly to do with this thing called nuclear fission. Neutrons are emitted, and they can be ionizing, but the major problem with neutrons is if another atom absorbs a neutron, because if it does, it will make a nucleus very, very unstable. And then what the other nucleus will do is it will then decay. When it then decays, it could give out alpha, beta, gamma. Few misconceptions. Some people think that a nucleus can only give out either alpha, beta, or gamma. It could give out one, it could give out two, it could give out all three of them. Usually alpha is where you have a very large nucleus. Beta is where you have a nucleus that has a lot of neutrons in it. Gamma, again, is just from the nucleus when it's changing energy levels. All three of these are released from the nucleus. So don't say the atom, it's the nucleus. So important. Now this bit of kit is called a Geiger counter. Actually, that thing there, that is the Geiger counter. This thing here is called a Geiger-Müller tube. This thing, the Geiger-Müller tube, is where radiation gets detected. The Geiger counter merely just picks up on how many times it's being detected, either in a certain amount of time or per second. So whenever we're using a bit of equipment to measure how radioactive something is, how many times a second it's decaying and giving off radiation, we use one of these bits of equipment. But yes, Geiger-Müller tube. So that pen's not working. Come on. That's the Geiger-Müller tube, and that is the Geiger counter. Hans Geiger. So yeah, as we said earlier, alpha, paper, skin, a few centimeters of air, it can't go through. Beta, 3 to 5 millimeters of aluminium. And lead and concrete reduces gamma. Okay, so now what we're going to do is we're going to look at some of the properties and how they actually link to the structure. Now this is the first one, to do with electric fields. Electric fields you may have done, you may not have done in P2, electricity. Electric fields, what they will do is they will cause a force on a charge. So this is the reason why if you have two, let's say, electrons together, they repel each other, because they're in each other's electric fields. Now if you look, here is the electric field here, these blue lines. The electric field is going that way. In the electric field, the arrows point in the direction that a force is occurring on a positive charge. So if we have all these types of radiation coming in here, we've got alpha on the right hand side, beta on the left, and gamma here. Alpha, its trajectory changes going to the right because it has a positive charge. So therefore, the force it feels is going that way, so it starts to curve over here in this direction. Beta has completely the opposite charge, so it curves in the opposite direction over that way. The force is this direction. Finally, gamma is completely undeflected because it has zero charge whatsoever. Some people might be wondering about the fact that if you look at both of these, an alpha and beta, they are going in the opposite direction, yet you would have thought that alpha would be deflected a bit more than beta. True. We've got to take mass into account as well as charge. These aren't exactly what happens. You just need to know the fact that alpha will go one way, beta will go the other, and gamma is not deflected because it has zero charge. So alpha, the force is felt in the same direction as the field lines, beta in the opposite direction, gamma undeflected. And this is what we do in order to determine the charge and basically the type of particle in particle accelerators. Now we're talking about earlier ionizing strength. We said that alpha was the most ionizing, then beta, then gamma. The reason is, well, this is what ionizing is. If alpha comes into an atom, it will literally just knock an electron clean off that and turn this from a charge that was neutral into a charge that is now +1, i.e. an ion. It removes an electron from the atom because it's got a lot of momentum. Alpha is traveling relatively fast, but it's got a lot of mass as well, so it's very easy to do that. Beta has got momentum, but not as much as alpha, and gamma does have momentum. It seems a bit weird, but not as much as the others. I always say it like, imagine that someone is holding a ping pong ball in their hand, and imagine you're throwing at them 4 basketballs, and these basketballs, they're attached to each other. Imagine someone threw that at you with a ping pong ball on your hand. I'm not going to embarrass myself with drawing a hand. That's very easily going to knock that electron clean off your hand. Let's say that this electron is actually modelled by a ping pong ball. So if you imagine I've got that ping pong ball in my hand, the electron, and I throw another ping pong ball, chances are I'll probably be able to knock that off with enough goes, but not as easy as if I had 4 basketballs. If you imagine with ionizing radiation, this is literally what's going on. If you're taking an electron off an atom, what you're doing is you're changing that atom into an ion. If you're doing that to DNA, what you're doing is you're mutating that DNA, you're changing it. That mutation can therefore lead to a different protein being made. It might be the wrong protein, or it might be that the protein's being made incredibly fast, and therefore you get a tumor. So we said that ionizing radiation leads to a mutation. That mutation leads to a cancer cell being formed. Key thing to note about radioactive decay, it's completely random. Now what that means is this, so I've got lots and lots of uranium nuclei here. Say lots, I think it's 40 there, yeah, there's 40. These things are very unstable, they're going to decay. Try and have a guess at which one you think is going to decay. It's that one. And that one. And that one. And that one. The thing is about decay, it's completely random. You cannot predict when a nucleus is going to decay. On average, we can predict when half of these are going to decay and how long it's going to take, but you cannot predict exactly when one nucleus will decay. So that is why it's completely random. As you can see by these, it's giving off alpha radiation as well. And when things do decay, they can change. So because we've got this uranium here giving off alpha, which is 2 protons and 2 neutrons, the atom itself is going to change. And this is why we get it changing into things like thorium. We'll come on to these radioactive decay equations in another session. So this is what I normally say to my class. I say, right, you've got 3 cocktails here. One of them is an alpha source, one is a beta source, and one's a gamma source. The idea is you want to survive. Which one of these would you like to drink? So, pause the video. Which one would you like to drink? You want to survive. The answer is this one. People normally go for beta because it's blue and it looks nice, but gamma is the safest. 2 reasons. Gamma, it is the least ionizing. So if that's in your body, it's going to do the least damage. If alpha is in your body, it's going to do the most damage. Second thing, gamma, if it's only reduced by lead and concrete, it can get through flesh nice and easy. But alpha is stopped by things like skin. So the alpha is just going to stay in your body, bounce around, damage more and more nuclei. Ionize more nuclei, damage more cells, causing more cancer. So if, guys, you ever have this choice in life, if someone says you've got to drink one of these, go for gamma. Right, final thing, identifying the type of radioactive decay from a source. So, typical question you'd get is that you will get a radioactive source and you will have a detector. Detector, oh come on, that's not a detector, that is a Geiger tube, and that is a Geiger counter. So, you will have this setup, and this will be picking up radioactive decay coming from the source. It may be alpha, maybe beta, maybe gamma, maybe a mixture of all 3 or 2 of them. Every time it detects it, or detects type of radiation, it will measure it on the counter. And they will have something called an absorber. Basically, they'll just put something in between the source and the detector, the Geiger tube, and you've got to use information they've given you to identify what type of radiation this source is giving out. So here's your typical question. So you've got radioactive source A, B, C, and D, and you've got to predict which type of radiation each one's giving out. Now they will usually do this without an absorber to start off with and then put different absorbers in the way. And as I said, you've got to try and work out what type of decay these sources are going through. It may be alpha, maybe beta, maybe gamma, maybe a mixture. Press pause, see if you can work it out. Okay, so answers. Right, if you look at the first one, it looks like the radioactive count is different for these two. If anything, it's gone up. And you might be thinking, well, how the hell has it gone up? Has it become more radioactive? No, it's because radioactive decay is random. So you cannot predict when a nucleus is going to decay. So it might be the 1 minute it gives out 200, the next minute it gives out 202, the next it gives out 198. On average, it will be about the same. But if it changes by a small amount, that's fine. It may also be that you've got background radiation, i.e. radiation by natural sources around, things like stone. If you've got a radioactive source nearby, if perchance you have that, it may be a little different. But if you look at paper doesn't seem to be making much of a difference. So chances are it's not alpha. If you look at this, some people go, look, it's gone down by 1, therefore it must be beta. 1 is hardly anything. It's random, it's probably not beta. But now we put lead in the way, look at the difference. About 180, that's a massive difference. And that source there is probably giving out gamma. Second one, look, a massive difference there. Yes, that is probably it's giving out alpha. Not much difference there. Again, looking at randomness of this, probably not beta. And look, it's gone up again, so probably nothing. So the first one is gamma, the second one is alpha. Third one, it's going down by 22. That's quite a considerable difference considering we only started at 100. And look, these values at the start are different to each other. That makes no difference on what type of radiation it's giving out. So that, yes, is probably alpha. And look, another considerable difference, probably beta. Hardly any difference. Look, it's gone up again, randomness. This second source is alpha and beta. Third one, considerable difference here, so it's giving out alpha. Nothing much, it's gone up again, randomness, not beta. Quite a large difference here. It is, sorry, get rid of that, gamma. Now when you're doing this type of question, you'll get marks for identifying the type of radioactive decay it's going through, but also marks for your judgment. Why? In order to say things like, oh no, alpha, for source A, paper and aluminium seem to make no difference, but a dramatic difference by lead. Therefore, because lead is reduced by, gamma is reduced by lead, it has to be gamma. That's the sort of reasoning you need in this type of question. And you also don't need to do it as long paragraphs. You can just go A. A is gamma, massive reduction by lead. Lead reduces gamma. Okay, right. Enjoy, guys. See you next time.